Hello, everyone. Welcome to another Lunch and Learn of the SP Brazil Flow Assurance Technical Committee. I'm Thiago Silva, and I am the chair of the SP Brazil Flow Assurance Technical Committee. It's a great privilege to be here today at this Lunch and Learn. I'm very excited and have high expectations for the conversation we'll have here. So you are very welcome. So before announcing today's chairperson, I would like to invite everyone to join our Flow Assurance Committee chat on WhatsApp. If you are a flow assurance professional or interested in this topic, please scan the QR code on the screen and join the committee chat. You are very welcome. We will have another event in November. You are welcome to. Our agenda for November is very interesting too. We will see a presentation about applying composite coil tubing for platform-based remediation of flow assurance deposits in subsea risers and flow lines. And stay tuned for more information soon. Okay. So let's move on to today's presentation. I will call our chairperson, Osmari. Um, Let me see her mini bio here. Oh, here. So, Osmari is a petroleum engineer from the University of Zulia, currently employed by Baker Hughes as a production solutions advisor for Brazil. Over 16 years of oil and gas industry experience in artificial lift systems, ESP, PCP, SRP, formation damage identification, water conformance control, diagnosis of well production behavior, integrated analysis and wellbore simulations to understand performance and predict outcomes. So thank you, Osmari, and welcome.
Thank you, Tiago. Good afternoon, everyone. Welcome and thanks for joining us in today's session. I am Osmari Matera. I am the Production Solution Advisor in Baker Hughes. I will be your host today. It's a pleasure not only to be part of this Launch and Learn edition, but also be part of the SP Flow Assurance section of Brazil. In this edition of Launch and Learn, we will discuss a very interesting topic in the oil and gas industry, some production and integrity management in the oil and gas systems. We will have a participant specialized in this matter. So let me introduce you to the Dr. Sayamak Chirasi. He is a professor of mechanical engineer and the director of Erosion and Corrosion Research Center at the University of Tulsa and director of the Sand Management Project in the same university. Professor Chirasi has contributed to over 700 publications, technical and invited presentations, most of them related to erosion, corrosion, and multi-phase flow for the renewable energy and oil and gas industry application. Professor Sirashi passed 35 years of teaching and research at the Tulsa University, has advanced the state of art in the important field of erosion mitigation for oil field applications, and he is known worldwide through his work for the sponsor of the research and through this publication and short courses delivered around the globe. So once again, Professor Sirasi, welcome. The mic is yours.
Thank you. Thank you for inviting me for this lunch and learn. And I hope all can hear me okay. Yes.
Yes, we
And
can hear you.
looks like you have shared my screen already. So let me go to the presentation mode. Uh, can you see my slides in presentation mode? Yes, I cannot hear. Can you hear me?
Yes, yes,
Okay, all
Professor.
right. Just
It's
want to
oh,
just want to double check and make
yeah,
sure.
sorry
Yeah,
about
no
that.
problem. Okay, all right. All right. Well, thank you again for inviting me for this lunch and learn. Uh, originally I had a short presentation, but they gave me an opportunity to speak longer. So I put some slides together related to what we do at Erosion Corrosion Research Center and also the Tulsa University sand management projects. I have many associates that work with me as professors and also some research associates, some of them full-time, some part-time, have been contributing to a lot of work that is ongoing right now. Just to give you a little bit of background on Erosion Corrosion Research Center, we started the ECRC in 1983, and it has been a continuous consortium. ECRC was originally formed to develop guidelines to replace the API RP14E. Some of you who have been in flow assurance for a long time, you may hear about uh, uh, Erosion Corrosion Research Center and also API RP14E. Our objectives at ECRC is to provide design and operating guidelines through our research results, and we have developed some computer programs that are very unique in this area. One of them that some of you may know, is called SPPS, Sands Production Pipe Saver. It predicts erosion, solid particle erosion. It accounts for many materials, different particles, and also some geometries. And also we have included recently a machine learning module, artificial intelligence machine learning module, which is based on experimental data. But the SPPS that I will discuss briefly is a mechanistic model that calculates erosion. We also have another computer program for calculating liquid impact erosion. It's called LISE, but the acronym is not really representative of the actual model. It calculates the liquid impact erosion. We also did a lot of work on CO2 corrosion, especially earlier in time, and we have a CO2 corrosion model. And I know some of the corrosion specialists at Petrobras have been using this, and also looking at the erosion corrosion model, which we can handle CO2 corrosion and the effect of sand and also calcium carbonate on corrosion, and also removal of the scale. Just to give you an overview of what SPPS can do, I think this graph may give you some idea. For example, on the vertical axis, we have the liquid rate, and on the horizontal axis, we have the gas rate in millions of standard cubic feet per day. And we have calculated erosion for a specific case. As you can see, this is a 10-inch carbon steel pipe, and it's a long radius elbow. There's an elbow, and the gas molecular weight, pressure, 1000 psi, and then the condensate, so the wet gas, and the water cut is say 15%. So these are some flow conditions that are given, and based on the flow conditions and the sand rate, for example, in this case, the sand rate was assumed to be very low, 0.1 kilogram per day, we can calculate what is actually the solid particle erosion on an elbow. So this line here represent erosion of about 5 mils per year. I'm sure some of you know what is mils, is 1/1000th of an inch. So 5 mils per year is pretty small, in the order of 0.16 millimeter per year. So, and then what happens is this curve tells us if we are to the left of this, if we are to the left and below this curve, then our erosion would be less than 5 mpy. And if we are to the right, then our erosion would be greater than 5 mpy. So it's erosive conditions. And as you can see, we can tell you what are the safe operating conditions. And here's a prediction from the API RP14E with a C value of 100. And as you can see, there is a lot of region here where erosion may not be a problem for a very low sand rate, but API would prevent that. So it could be very conservative when there is a low or no sand production. And if there is sand production, then it cannot really predict erosion as a result of sand production. So this is one of the application of the model, SPPS model that we have developed, and we can easily produce graphs like this for various operating conditions. Now, another software which is calculates the liquid impact erosion. This is for a situation where you may have some gas at high speed and very low, some low liquid and maybe no sand even. So for this case, we can use this other software and calculate what's the erosion as a result of the droplets. So here we have the erosional velocity as a function of pressure. And as you can see, the API RP14E tells us that our erosional velocity should decrease when the pressure is higher. But the models for erosion and also for liquid droplets impact says that our erosional velocity increases because the density of the gas would prevent or would reduce the impact speed of the droplets or particles. So as you can see, API RP14E, even the trend of it for multi-phase flow does not agree with physics. So it cannot account for liquid droplets or sand. So as you can see, it has a lot of limitations. And over the past 35, 40 years, where we have been looking at erosion issues, we have developed a model for calculating erosion rates. And I know some people at Petrobras are also using the model. And there is a lot of work ongoing right now, even to upgrade SPPS. For example, we have two versions of SPPS, 1D and 2D. Is actually it tracks particles on before we get into an elbow, and it calculates, the velocity of the impact of the particles. So it's a mechanistic model, and it's not only for elbows, but we also have other geometries. For example, we are looking at gradual contraction expansions that you may see in well bores. As I mentioned, we have a artificial intelligence model, and we also work on CFD, a lot of CFD. We have developed a lot of expertise in predicting erosion with CFD, and we use that for larger pipe diameters where we cannot do experiments. And we also have been developing uncertainty model. Actually, this work was done by encouragement of Petrobras, where they wanted to see what are the uncertainty model for our erosion model. As I mentioned, we have a liquid droplet erosion, and we also are running additional experiments with liquid droplet. We are working on different bend radius and under multi-phase flow conditions. We are running experiments with liquid and gas, liquid dominated, and also looking at the small particles, uh, you know. So while we have this erosion model, there is room for improvement. For example, looking at elbows in Sirius, where we have more than one elbow following each other. And then also improving erosion models that are used in CFD. And also SPPS is an Excel VBA based model, but we have also developed the Python version of this. So as you can see, lots of work is even ongoing right now to upgrade our erosion model. We have a facility at University of Tulsa that we use, 2-inch, 3-inch, or 4-inch pipes on this boom that we can run experiments in horizontal and also vertical conditions. The length of this is about 18 meters. So for multi-phase flow, and this is a 4-inch test section right now. And we also, as I mentioned, we run erosion tests for different two elbows following each other. So we can vary the distance between the two elbows and look at the erosion of the second elbow as compared to the first. And we have different ways of measuring erosion. These, for example, early in time, we use erosion specimens. And now we are making erosion measurements using fixed mounted UT ultrasonic sensors. So there are different technology that we use for erosion measurement. Also, we have different test sections or flow loops. Here is an experimental facility that we use for a slug flow conditions, and we have a slug catcher. Here's another test section for a liquid dominated, which is right now is a 3-inch test section. And as I mentioned, we use a different technology. Here, for example, we use a template to measure erosion thickness losses at many different locations. And we also have some acrylic test sections that we can paint the interior of acrylic and then look at the erosion pattern to make sure we are measuring erosion and we use ultrasonic handheld sensors, and also, as I mentioned, we have fixed mounted sensors that we also use for erosion. So if we have, say, many fixed mounted ultrasonics, we can look at the erosion. In this case, this was, you know, many different flow conditions. We run a lot of experiments for a lot of gas dominated flow conditions and so on. And here, just want to show you one sample of a type of experiments that we did for different R over D of 1.5 up to R over D of 5. And then we also run experiments doing flow visualization on similar using acrylic elbows. And of course, we did many different flow conditions. Here is one example where we use 75 micron sand. very small volume concentration, 0.002% particles, 80 kilogram of sand throughput, and the gas velocity was about 31 meter per second. So we can, after making the wall thickness measurements, we create these contours, looking at erosion and see how the location of the maximum erosion changes with different flow conditions. This was just gas, but we have run these experiments with multi-phase flow and so on. So as you can see, we conduct experiments. We also do a lot of modeling utilizing CFD, and also we do mechanistic modeling where we create simplified flow conditions. And right now, this our SPPS model that some of you may be familiar. It calculates erosion in elbows, including long radius elbows under multi-phase flow conditions. We are conducting experiments right now on plug T's here, and also some T. A straight pipe, there are not a lot of data on a straight pipe. The erosion of a straight pipe is a lot smaller than elbows. So most of the time we look at geometries that erosion are higher than a straight pipe, like impingement, direct impingement, sudden and gradual expansions, contractions, plug T, and so on. So this is what we have developed, is SPPS, just to show you some validation, if you will, of this SPPS. This is some erosion data that, CFD predictions. As you know, with CFD, we can predict flow velocities, and then we use particles and see where the particles are impacting. And then we have erosion models, so we can predict erosion utilizing CFD. And some of you familiar, especially in multi-phase flow, is very time consuming to obtain flow results and erosion results with CFD. But, and here are predictions of erosion in the units of thickness loss per kilogram of sand. And as you can see, this is over 7 orders of magnitude of erosion. And then here is the one-dimensional model that we have used, utilizing 2 different models within that SPPS, the latest SPPS version. And as you can see, over a wide range, we can match the CFD results, and these results are obtained by a couple of minutes. But each of these CFD results took a lot of time to produce. We also, as I said, we run experiments, lots of experiments. This was early in time, where we look at other experiments at AEA, DNV, Kumar, with some experiments at very small particles, and also some other data. So as you can see, our one-dimensional prediction matches the data, again, very well over a wide range of erosion data. Here is some experiments that we have conducted on the horizontal axis. And then this was just an earlier version of SPPS model, the blue, and the best fit line, as you can see, is passing through pretty much most of the data. And another prediction from DNV is shown by red. And DNV, some cases, DNV model was not very well. It was under predicting. But as you can see, this model, the R square, was a lot better than another model utilizing DNV for lots of experiments from 2-inch to 4-inch, and even there is some data on 5-inch. And here, for those all those CFD cases that I showed you earlier, the DNV results are again under predicting the observed erosion with CFD. So, and these are the R-squared cases. This includes large diameter, high pressure, high viscosity conditions. So the tool that we have developed is very well received. It's right now our ECRC members, they have access to these SPPS software programs. The companies are benefiting from 40 years of research, the members. And right now we've got 17 actually members, and each company pays 1/20th of the cost. So there is a lot of feedback and also advantages for the members of ECRC. And Petrobras, I know, is a member. There may be some other companies in Brazil that are operating. And for the information, for last year, our membership is about a very modest membership fee. And if a new company joins, they have to pay equipment fee and so on. Over the years, many companies have contributed and also were a member of or have been. Some of these companies right now, they don't exist anymore, or they have joined the companies. But as you can see, all pretty much many oil and gas and service companies have been a member of ECRC. So many students, PhD, MS, and also research associates have contributed to the modeling work that we have done. Now, I wanted to also tell you a little bit about, I could give lots of examples, but really this time is limited. So I just wanted to also tell you about some activities of another consortium. It's called TUSMP, Tulsa University Sand Management Projects. And TUSMP was established for other issues related to sand production. For example, what is the velocity that is needed in case you produce sand particles or other particles? What are the velocities that are needed to transport particles? Also, there is a lot of interest in detection using different types of equipment of sand or erosion. And also for this TUSMP, we have developed some modeling based on a lot of experiments that have been conducted. Wanted to give you some examples on sand transport, which we are using to predict the velocity, critical velocity that is needed to move particles. And this is, you will see that we also have a machine learning module that is only based on experiments. We have 2,200 data points, so we took advantage of this significant amount of data, and we developed a machine learning model that I'll briefly discuss. We also have another work in progress that is called threshold sand rates. And this model is for acoustic sand monitors. As you know, many companies are utilizing acoustic sensors to look at the impact of sand particles. So if there is a sand production, they can detect the sand production. Also, some companies are hoping to use acoustic monitors for even determining what is the rate of particles that are being produced. So these are, so we have been developing some software to predict what is the threshold sand rate that acoustic monitors can detect. Also, there are some related programs. Acoustic is a computer program for calibrating acoustic monitors. And also, there's another model is if you have an electrical resistant probe that is measuring erosion, can we predict the sand throughput? So we have developed these models, and also there are some guidelines that have been developed through our research. So I briefly will talk a little bit about this, uh, uh, some of the activities of sand management project is we have been looking at commercially available sand and erosion monitors, acoustic monitors, erosion monitors, even some optical devices for sampling sand. And we have developed models and tools to help interpret output from sand and erosion monitors. And as I mentioned, another work is looking at critical velocity for transporting particles and developing guidelines. So first, I wanted to just show you a little bit of work on sand transport. I'm not going to be able to, but I wanted to acknowledge Dr. Vieira, who did lots of work. He was a postdoc research associate. Now he's with ExxonMobil. And also we have Dr. Wong is contributing right now to the sand transport modeling. We have lots of experiments, database. Basically, again, critical velocity is the velocity needed to move solids and prevent accumulation of solids. And we have lots of data. Single phase is if you have gas or liquid with particles, and multi-phase, of course, you've got gas, liquid, and particles. We have data with horizontal. Normally, in vertical pipe is easier to move the particles than horizontal flow, and also some inclined. So we have lots of data, about 1,700 data points for gas and liquid with sand, and some data with inclined. And some, as you can see, lots of the data has been collected by our consortium here at Tulsa, and lots of data on multi-phase flow and some in inclined flow conditions. And we have run experiments where in 2-inch, 4-inch, looking at the velocities that are needed, again with gas and liquid. Here is just one example of looking at inclined pipe and then running some experiments with inclined. Right now we are doing that in a 4-inch pipe. And basically we have developed a model based on looking at velocities that are needed to move the particles. So here we are looking at forces that are acting on the particles, and we can account for different types of there are different types of transport. For example, disperse or scouring. We are using a model that says what is the minimum velocity that is needed so the particles will not stop even, and so on. And we have done, looking at force balance, and then we have also we have developed a constant that accounts for a Stokes number, and that has made the model to be very successful, because, as you know, a Stokes number accounts for uh, if the flow is able to pick up the particles or not. Is the reaction of the particles to the flow. So a Stokes number is used as one of the modeling constants. And here, just to give you a very short presentation of the predictability, here on the horizontal axis for these graphs, we have the sand concentration in ppm and the critical velocity, liquid velocity for different types of particles, 600 micron, 300 micron, and the red is the model, and the black symbols, circles, are the data. So as you can see, for over a wide range of particle sizes, we can predict so if you're below this line, you have sand dunes or even a bed can form. And above these lines, we are pretty sure that we are moving all the particles. And as I mentioned, this has been done in multi-phase flow. Here, I just wanted to show you some images of when you have sand dunes. Now, our model is a velocity that is needed so that there is no dunes. But here, I wanted to show you that for a wide range of velocities, you could even transport particles, but the particles are moving in a form of a dune that you could see here. They have a heart shape. And as the velocity increases, the dunes are getting smaller, and eventually they will disappear because all the particles are moving all the time. Just to tell you, we also look at different multi-phase flow regime. For example, in a slug flow, we have to see what is the holdup of the slug unit, and then what is the average velocity of the slug, and see if this velocity is greater than the critical velocity that is needed. If so, then we do some iteration on VSL, and then given the VSG, superficial gas velocity, we iterate on VSL. Another flow regime where we have issues with sand transport is a stratified flow. Again, a similar modeling approach is used for the stratified flow, where we look at the velocity of the liquid that is needed to move particles. So anyway, there's lots of modeling work in progress, but I wanted to just show you a couple of results. Here, just a 2-inch pipe, very small particles, and horizontal flow. And the data is shown by, as you can see, this is a flow regime map, VSL versus VSG. And a slug flow region is here. Below the slug flow, in this black line, we have a stratified flow, a stratified wavy, and a smooth stratified. And as you can see, the data for sand transport or for horizontal pipe are mostly for a slug. When we have higher velocities, of course, the sand is transported. But as you can see, we have the data, and this blue line is the TOSMP that operates in a slug and then is transitioned to the stratified flow. And as you can see, the model we have developed is a good match to the data. And there's some other popular model, Danielson model and Angelson, and also Salama. But as you can see, the model we have developed is the best match to the data. And here for a 4-inch bigger particles. Again, a similar type observation that the model we have developed is again a good match to the data. So so we have a mechanistic model, and I could tell you a whole lot. Right now, what we are doing is we are also looking at the velocities that are needed to move a bed. So this is the type of work that we are doing right now. And I know I'm running out of time, but it's we have lots of data, as I mentioned. So we have also developed a machine learning model for both liquid sand and gas liquid. And as you can see, for the machine learning models are good match, of course, to the observation. So I'm not going to do the demonstration of the program, but we have a model that produces this curve here. And it tells you that, for example, this is a superficial liquid velocity versus superficial gas velocity. And we can define the region for which you may have a sand dune or bed, and then a region of sand transport. And not only we can apply this model to even a lot larger pipe. For example, here there was a field data that they observed that in the current operation, in an 8-inch, they would have some sand, and there was some evidence. But then in their future operating conditions, the sand would have been transported very effectively. So this is another work, and I wanted to just very briefly tell you about this uh, uh, sand detection. Also, we put sand detection sand sensors downstream of elbows and also in horizontal sections, and these are acoustic monitors that we install and in different flow loops. Just want to show you one sample data, and then let you see, guys, to see if you have questions. So, for example, here we have installed the acoustic monitors, and we are looking at the raw data from the acoustic monitor. This was just liquid with 21 feet per second in a 2-inch pipe. And as you can see, with no sand, we are detecting some variations. And then we are gradually adding more and more sand up to about 0.25%. Sorry, 0.25%. And as you can see, this is the average of the background noise. And then this is 2 sigma above it. So for very low sand concentration, the signal from the sand monitor is not large enough so that you could see it. But if the sand concentration starts increasing, then we can see that this background, the sand acoustic values are above the detection limit of the sand. So we run lots of experiments with different type of flow conditions. Here I wanted to show you one in annular flow in a 4-inch pipe, 0.1 meter per second. We have collected lots of experiments, but I just want to show you some sample one. This is 300 micron, and this is horizontal even. So as you can see, again, here's no sand, and then we can then look and see how the effect of sand concentration, the monitor output changes with sand concentration. And then same experiment, maybe with 25 micron sand, again in the same flow regime. But look, for 25 micron sand, as you can see, we're we see a gradual, for some cases, increase. So when we have even 1% sand, you would not perhaps notice when you have a very tiny particles in your flow. So we have lots of experiments that, and in a slug flow, even 75 micron particles, as you can see, with a slug flow, we get lots of, uh, impacts of liquid and particles also too. So we are running lots of experiments, doing analysis on the experimental data, and we are developing a tool for predicting, and also we do flow visualization. Uh, as I mentioned, I'm running out of time, but I could, spend hours discussing some of the observations, and also we visualize the flow. For example, for this flow condition that was 5 meter per second of gas on 0.1, as you can see, that if we have particles in the flow is pretty smooth and there's very little impact here. So it's very hard to see particles in such a flow regime. And then, but in a higher velocity, like 30 meter per second, as you can see, lots of liquid droplets. And if you have particles, lots of particles will impact the pipe, and the acoustic monitors will pick them up, and so on. So we do flow visualization, and lots of work is in progress with experimentation, looking at different particle sizes, looking at different type of acoustic monitors. And also we do, as I mentioned, we do some modeling. And finally, based on many experiments that we have developed, we are creating a machine learning model which can predict what is the threshold sound rate that acoustic monitors can pick up. So the membership of this GIP right now, we have Petrobras is smaller than erosion corrosion, but right now we've got 8 companies that are supporting the TOSMP GIP. So I know that there's not much time for questions, but I could address perhaps a few questions, and then I have to run to my class to teach. So again, thank you for your attention, and again, thank you for your invitation. I'd be able to maybe address a few questions.
So, Professor, thank you very much for this enriching presentation. We will now, given the short time, we will have a space for just one question. So, Fernando Guama from Shell asked the following question. Given that most erosion models are made for simplified geometries and predominantly single or two-phase flow regimens, what are the main challenges and methodological strategies for ensuring reliability when these models are applied to complex production systems, such as choke valves and multi-phase flow line under transient conditions?
Okay, well, that's a very good point. For complex geometries like choke valves and so on, there is sometimes people do some CFD, computational fluid dynamics, but you still have to have an erosion model. So the erosion models that we are developing, people can use them, with CFD to predict erosion in complex geometries. But as I mentioned, also, we do handle erosion under multi-phase flow conditions. And for elbow, simple geometries, the modeling work is successful. But again, looking at chokes with multi-phase flow, for example, is very challenging type of issues. However, these simplified models could be used as a guide. If, for example, if you have some data, it could be used as a guide to help you understand, what parameters are contributing more to erosion. So I understand the simplified models cannot be applied to many complex situations, but at least for flow lines and many applications downstream, upstream, we could use these models to shed some light on the erosivity of the system.
Great overview. So we are short of time. Professor, let me thank you once again for sharing with us.
Thank you much. Appreciate that.
For sharing with us your expertise.
And you have my email address. If there is some interest, you could maybe contact me.
Great, sure.
Again, thank you for invitation.
Great. I think the main objective is to disseminate knowledge through these sessions, and we hope we could accomplish it. We want to thank everyone who participated and connect with us in this edition. Hope to see you soon in the upcoming sessions.
Thank you. I got to run to my class, so thank you much.
Thank you. Have a great day, all of you.
Thank you.